In mid-February 1943, during the Battle of Sidi Bou Zid in Tunisia, German forces made a discovery that would echo through their engineering departments for the rest of the war. Among the damaged American vehicles left on the battlefield stood one fully operational M4A1 Sherman tank, its engine still running, its white star barely visible beneath the dust and battle grime. German soldiers quickly painted over the star with a black cross and claimed it as a prize. The name painted on its hull read, "War Daddy 2." This was no ordinary capture. The Sherman had belonged to Company G, 1st Armored Regiment, 1st Armored Division, and it represented the most modern example of American tank production at that stage of the war. When German mechanics inspected the vehicle, they found it intact in every essential system. The engine, transmission, radio, and even the gyro-stabilized gun were undamaged. Rather than disassembling it on site, they decided to drive it across the desert to a coastal port for shipment to Europe. That journey became legendary among those who witnessed it. The German crew drove the captured Sherman more than 350 kilometers across rough desert terrain to the port of Sfax, a trip that took 4.5 days. What stood out most was not the tank's speed or firepower, but its endurance. The engine never overheated, even under scorching desert temperatures. The transmission shifted smoothly without adjustment. The final drives and suspension handled rocky ground and sand without a single failure. German drivers, accustomed to halting every few hours to repair overheating engines or damaged gears on their own vehicles, were astonished by the American tank's consistency. The Sherman simply kept running. Every kilometer of that desert crossing undermined long-held German assumptions about American engineering. Many in Germany believed U.S. equipment was crude, built quickly without finesse. Yet here was a tank that defied those prejudices, simple in design, but remarkably effective. It did not need the careful attention or precision tuning that German tanks required. It worked because it was built to work, not to impress. By the time the Sherman reached the port, word of its reliability had already spread through German ranks. Officers of Heavy Panzer Battalion 501 described the machine as mechanically flawless. Engineers realized that the tank's behavior during the journey was as valuable as any technical data they could collect later in a laboratory. Orders soon arrived from Berlin. The captured tank was to be shipped intact to the Kummersdorf proving ground, the central testing facility for the German army, located just south of Berlin. There, specialists would study every component to uncover the secrets of its performance. The Sherman was loaded onto a cargo ship bound for Europe, its American star hidden beneath fresh paint, but still faintly visible through the desert dust. For German engineers waiting at Kummersdorf, it represented more than a captured vehicle. It was a chance to examine the industrial strength of an opponent whose factories were producing machines faster than Germany could replace its own losses. As the ship crossed the Mediterranean, preparations began for a series of detailed tests that would soon reveal an uncomfortable truth: that the American approach to building tanks, practical, standardized, and focused on reliability, had achieved something Germany's complex, precision-driven industry had never managed. The story of War Daddy the Sixth was just beginning. The captured Sherman arrived at the German port of Sfax, still coated in Tunisian sand, its engine and gears having endured the long desert crossing without a single recorded failure. To the German technicians overseeing its transport, this was already a revelation. Most German tanks, even when carefully maintained, struggled with long-distance movement. Yet this American machine had proven that endurance could be designed into a vehicle, not achieved through constant maintenance. Loaded onto a cargo ship, under strict orders to remain intact, the Sherman began its voyage north, across the Mediterranean. German officers aboard the transport ship noted in their logs that the vehicle's systems were checked daily and remained fully operational throughout the journey. The Army Weapons Office had made it clear the tank was to arrive in Germany exactly as captured, unaltered, so that engineers could study every feature. This was to be the most complete examination of an American tank ever conducted by the Reich's testing authority. By early spring 1943, the Sherman rolled off a rail car at the Kummersdorf proving ground, located about 25 kilometers south of Berlin. The facility was Germany's main center for technical trials of armored vehicles and experimental weapons. Almost every important German tank, from the Panzer IV to the massive Tiger and Panther, had been tested there. Now, standing among them, was a tank built by the Lima Locomotive Works of Ohio, a machine from an entirely different industrial world. As it arrived, German engineers signed it the testing number Versuchsfahrzeug 109 and painted a German military license plate WH058941 on its hull. Its American name, War Daddy Tuthen, remained faintly visible beneath the paint, a reminder of its origin. Teams of engineers, metallurgists, and automotive specialists immediately surrounded it. They began the methodical process of documenting every surface, every weld, every bolt. Armor plates were measured for thickness and angle. Gear housings were photographed, and even the screw heads were cataloged. Nothing was overlooked. The first impressions astonished the observers. The Sherman's construction appeared straightforward and logical, almost simple compared to the intricate designs of German tanks. The layout of components was practical, with easy access for maintenance. Electrical systems were clearly labeled, and wiring was arranged neatly, rather than buried deep within the hull. One engineer remarked that it looked more like an industrial machine built for daily use than a weapon of war. What shocked them most was how ordinary the craftsmanship appeared, and yet how well it all functioned. The Americans, it became clear, had designed their tank not for elegance, but for efficiency. Parts could be replaced quickly using standard tools. Bolted assemblies allowed rapid disassembly in the field. The Germans, who prided themselves on precision manufacturing and complex engineering, found the simplicity unsettling. To them, quality came from perfection and tight tolerances. To the Americans, it came from standardization and ease of use. The next phase of testing involved examining the powertrain, the engine, transmission, and final drives. Here the Germans encountered design principles entirely different from their own. The Sherman's Continental R9075 radial engine, originally derived from aircraft technology, ran with steady reliability even when pushed to extremes. Its air cooling system was simple but effective, and its filtration system prevented dust buildup far better than the ones used in German tanks in North Africa. The 5-speed transmission impressed the engineers even more. It used synchronized gears, allowing smooth shifting without the double clutching that German drivers had to master through extensive training. To a German tanker, accustomed to delicate gear changes and constant attention to the throttle, the Sherman's gearbox felt almost effortless. Each new discovery chipped away at long-standing assumptions within German engineering circles. They had believed American industry to be crude and unsophisticated, good at quantity, poor at quality. But the Sherman proved that reliability was not the absence of precision. It was precision applied differently. The Americans had built tolerances that were generous enough to prevent failure, yet accurate enough to maintain performance. The result was a machine that simply worked under all conditions. Within weeks, War Daddy II became the most closely studied tank at Kummersdorf. Detailed reports began to circulate within the Heereswaffenamt, the German Army Weapons Office, highlighting the differences in philosophy between the two nations' industry. German engineers began to realize that the true American advantage was not in any single feature, but in the system, the way design, production, and maintenance were all aligned toward one goal: keeping the vehicle running. The Sherman's journey from the North African desert to the testing grounds of Brandenburg marked more than a change in geography. It represented a turning point in understanding. German engineers, who once dismissed mass production as inferior, were now witnessing its power firsthand. They had captured a tank that embodied an industrial system built for endurance, flexibility, and simplicity, a system their own country could not easily replicate. The arrival of War Daddy the Sidi at Kummersdorf was the beginning of a revelation. The testing that followed would not only expose the mechanical secrets of the Sherman, but also reveal a deeper truth that in modern warfare, reliability and production mattered more than theoretical perfection. The Germans were about to learn this lesson in the most direct way possible, by measuring every part of a tank that had already proven, on the battlefield, that it was built to last. When testing began at Kummersdorf in the spring of 1943, the captured Sherman was treated like a scientific specimen rather than a weapon. German engineers approached it with a mix of curiosity, skepticism, and quiet apprehension. Many had read reports about American industrial capacity, but most still believed that German engineering was unmatched in precision and sophistication. Within days, the Sherman began to prove otherwise. The first detailed inspections focused on the hull and suspension. The engineers noted how the armor plates were cast and welded, rather than cut from rolled steel and joined with complex seams. This method, typical in American manufacturing, gave the Sherman's upper hull its smooth, rounded shape. At first glance, it looked crude to German eyes. They were used to sharp angles and carefully machined joints, but when they measured the armor thickness and stress distribution, they found the design was not only strong, but also efficient. The rounded surfaces deflected projectiles better than flat armor of similar thickness. Simplicity, it turned out, was serving a purpose. Attention then turned to the interior layout, and here the differences became even more striking. Everything inside the Sherman was arranged logically. The driver's instruments were clearly labeled in plain language, switches were easy to reach, and the controls felt intuitive. Even the storage racks for ammunition and spare parts had been designed with accessibility in mind. German tanks, though technically advanced, often suffered from cramped interiors and controls that required specialized knowledge to operate. In the Sherman, almost anyone with basic mechanical training could understand how the systems worked. The engine bay drew immediate attention. The Continental R97.5C1 radial engine, originally an aircraft engine adapted for tank use, was surprisingly compact for its power output. Air-cooled and reliable, it delivered around 400 horsepower, modest by German standards, but remarkably consistent. The cooling system required little maintenance, and the oil filters could be replaced quickly in the field. The engineers ran the engine for extended periods, testing it under load and recording temperature readings. Even at high revolutions, the engine remained within safe limits. There were no signs of overheating, no oil leaks, and no vibration that indicated imbalance. For the Germans who struggled constantly with the complex and temperamental Maybach engines in their own tanks, this performance was both impressive and humbling. The next discovery was found in the transmission, and it was the moment that truly surprised them. The Sherman used herringbone-cut gears, a design that distributed load evenly across multiple gear teeth. This type of gearing had been used in the American automotive industry since the 1930s, but had never been widely adopted in German tank construction, because it was considered too difficult to mass produce. Yet here it was, perfectly machined, running smoothly without noise or grinding. The gearbox offered 5 forward gears and 1 reverse, with synchronization from second to fifth gear. This meant that drivers could shift smoothly without double clutching, a convenience that reduced training time and mechanical stress. German tanks, by comparison, relied on unsynchronized straight-cut gears that demanded precise driver skill and frequent repairs. One of the engineers wrote in his report that the American gearbox demonstrates a philosophy of reliability unfamiliar to us. He noted that while the components lacked the fine tolerances seen in German designs, they achieved durability through intelligent engineering and stress distribution. The Americans, he realized, had not built perfection into each part. They had built resilience into the entire system. The suspension system also impressed its examiners. The Sherman used the vertical volute spring suspension, VVSS, a simple yet robust mechanism that absorbed shocks from uneven ground remarkably well. It was easy to repair, required no specialized tools, and could be replaced in the field with minimal effort. German tanks, by contrast, employed complicated interleaved road wheels and torsion bar suspensions that performed well on paper but clogged easily with mud and ice. Field maintenance crews in Russia and North Africa knew how frustrating these systems could be. The Sherman suspension was not sophisticated, but it worked everywhere, all the time. Perhaps the most surprising realization came from how the Sherman had been assembled. The engineers could tell that many components came from different suppliers. Some parts bore marks from Lima Locomotive Works, others from Ford or Buick, yet everything fit together perfectly. Interchangeability was complete. A transmission built by one company would fit seamlessly into a hull built by another. This level of standardization was something German industry could not achieve. Each German factory introduced small variations in design, making parts from one plant incompatible with tanks built elsewhere. It was a costly inefficiency that grew worse as the war dragged on. As days turned into weeks, the engineers' initial skepticism gave way to quiet respect. The Sherman was not a miracle of design. It was a triumph of practical thinking. It represented a nation whose industrial power rested not on perfectionism, but on process, organization, and scale. The Americans had taken lessons from their vast automobile industry and applied them directly to warfare. The result was a vehicle that did not need to be the best on paper. It only needed to work every single day. By the time the initial inspection phase concluded, the reports from Kummersdorf painted a clear picture. The Sherman's advantage was not its armor or its gun, but its mechanical reliability. Its systems were designed for soldiers, not for engineers. Its parts were built to be replaced quickly, not repaired endlessly. For the German officers reviewing the findings, the implications were deeply troubling. If this was what the Americans could mass produce by the tens of thousands, then Germany's emphasis on technical perfection might have been a dangerous mistake. The first impressions of the Sherman had done more than reveal an enemy tank's secrets. They had exposed the limits of an entire industrial philosophy. When the first phase of inspection ended, the engineers at Kummersdorf prepared for what they called the operational evaluation. The objective was simple: to measure how the captured American tank performed under controlled stress. Every major system, engine, transmission, suspension, and steering would be pushed to its limits and compared directly with the newest German designs. The tests would be long, methodical, and brutally honest. The Sherman was fueled, rearmed with dummy ammunition for balance, and driven onto a wide test field south of the main proving ground. German officers, technicians, and representatives from the armaments ministry stood by with notebooks and stopwatches. Across the field waited two German machines, a brand new Panther Ausf Day and a Ferdinand tank destroyer. Both represented the height of German engineering in 1943. Powerful, heavily armored, and equipped with advanced weapon systems. The Sherman, by comparison, looked modest and unremarkable. Yet within hours, appearances would lose all meaning. The first trials were basic driving tests: acceleration, braking, and gear shifting. The Sherman started cleanly and moved off with a steady hum. It accelerated evenly, each gear change smooth and unforced. The synchronized transmission allowed shifts that felt almost civilian in character, something unheard of in German tanks. The Panther followed with a roar from its Maybach HL230 engine, its acceleration more dramatic, but its gear changes rough and deliberate. The driver had to use both hands to guide the lever through the heavy gearbox. The Ferdinand, equipped with an electric drive system that transferred power from its twin Maybach engines to electric motors at the rear, moved forward heavily and awkwardly. On uneven terrain, the difference became clearer. The Sherman's suspension absorbed bumps with surprising smoothness, keeping its tracks tight and steady. It was not fast, but it was consistent. The Panther's advanced torsion bar suspension, gave excellent stability, but was very more sensitive to maintenance issues. The Ferdinand, massive and overloaded at nearly 65 tons, struggled. Its weight dug deep ruts into the soil, and every sharp turn strained its steering system. When the engineers conducted endurance trials, the Sherman began to reveal its true strength. Over several days, it was driven for hundreds of kilometers across roads, gravel tracks, and cross-country terrain. The crew monitored engine temperatures, oil pressure, and transmission performance throughout. The data recorded a remarkable pattern: stable temperatures, consistent fuel consumption, and almost no mechanical wear. After each run, technicians opened the engine compartment, expecting signs of stress, but found none. Bearings were clean, gears showed minimal abrasion, and oil levels remained within tolerance. German officers, used to stopping their own tanks every few hours for adjustments, found this difficult to accept. The Panther and Ferdinand both required maintenance during the same trial. The Panther's transmission overheated after just a few hours, forcing the crew to let it cool before continuing. The Ferdinand's electric system malfunctioned repeatedly, each time requiring a halt for inspection. The Sherman, by contrast, simply refueled and kept going. The engineers were meticulous in their measurements. They recorded the torque output of the transmission, the temperature of the cooling system, and the vibration levels of the engine mounts. Each result supported the same conclusion: the American tank had been built for continuous use. It was not elegant or advanced in design, but its reliability was undeniable. The simplicity that once looked primitive now seemed brilliant. The high point of the trials came in early June 1943. During a large demonstration attended by senior figures from the German armaments industry, including Albert Speer, the Reich Minister for Armaments and War Production. The event took place at the Hillersleben Artillery and Tank Range, where German and captured Allied tanks were tested in front of military and industrial leaders. The purpose was to showcase progress in German tank design and to evaluate foreign machines. The demonstration began with hill climbing trials. The Sherman was first. It approached the slope steadily, shifted through its gears with no hesitation, and climbed smoothly to the top. The driver did not struggle. The tank moved as if on level ground. Next came the Panther. Its powerful 700 horsepower Maybach engine gave it speed, but the gearbox resisted the driver's efforts. It reached the top, but only after a noisy, difficult ascent. Finally, the Ferdinand began its climb. Its engines roared, then sputtered, and halfway up the vehicle stalled. The massive tank destroyer slid backward, immobilized. Recovery crews rushed forward while the observers looked on in silence. The scene left a lasting impression. The vehicle, meant to symbolize German technological superiority, had failed in front of the country's most important industrial officials. Speer, known for his realism, understood the implications immediately. If American tanks could achieve equal performance with far simpler construction and better reliability, then Germany's production philosophy needed to change. Reports from the demonstration circulated within days. Officially, they praised the Panther's potential and the Ferdinand's firepower. Privately, they acknowledged the Sherman's reliability and ease of operation as remarkable. Speer later admitted in his post-war writings that he had been surprised by the American tank's cross-country mobility and its ability to climb slopes considered inaccessible for vehicles of its type. Field reports from Italy and the Eastern Front would soon confirm those observations. The engineers at Kummersdorf continued their analysis. After the demonstration, they disassembled major components to study wear patterns, measured tolerances, and compared them with equivalent German parts. What they found deepened their respect for American engineering. The gears, though manufactured with looser tolerances than German standards, showed even wear and no signs of stress failure. The engine bearings were standardized components similar to those used in civilian vehicles, easily replaceable and inexpensive. The electrical systems were simple, redundant, and reliable. Every examination led to the same uncomfortable realization: the Americans had solved problems the Germans had not even recognized as critical. While German designers chased higher performance, the Americans had built endurance into every component. By the end of the trials, the conclusion was unavoidable. The Sherman's design philosophy was fundamentally different, and in practical terms, superior. It did not aim for perfection. It aimed for functionality. It accepted that soldiers in the field would not have factory tools or expert mechanics, and so it gave them a machine they could rely on. For the engineers at Kummersdorf, who had grown up in the tradition of precision and technical pride, the experience was humbling. They had witnessed a tank that did not rely on genius or complexity, but on consistency, a product of an industrial system built on standardization, training, and experience. The Sherman's trials had proven that sometimes the greatest strength lies not in sophistication, but in simplicity that never fails. The results of the Kummersdorf trials spread quickly through technical circles in Berlin. Copies of the reports were circulated among senior officers, factory engineers, and officials of the Army Weapons Office. Each page told the same story. The American Sherman had outperformed expectations in every reliability test, while the newest German tanks continued to suffer from mechanical fragility. At first, many refused to believe the findings. Some claimed the captured tank was a rare example, carefully built by the Americans for demonstration. Others argued that the results were exaggerated or that the test conditions had favored the Sherman. But as more data arrived from repeated trials, the numbers became impossible to deny. The American tank consistently ran for thousands of kilometers without major failure, its engine and transmission showing wear far below what the Germans considered acceptable. What unsettled the engineers most was the simplicity of the construction. Every part of the Sherman seemed to have been designed with maintenance in mind. The crew could remove an engine component or a gearbox cover using basic tools. Electrical systems were modular. Components could be swapped easily. Bolts, hoses, and couplings followed standardized dimensions. Nothing required specialist adjustment. German tanks, by contrast, were masterpieces of precision that demanded expert care. A small mistake by a mechanic could disable an entire vehicle. By the early summer of 1943, the engineers who had conducted the tests understood the full implications. Germany's design philosophy was trapped by its own standards. Every improvement in power or protection added complexity and reduced reliability. The Panther and Tiger had formidable guns and thick armor, but their transmissions and final drives broke under the strain of their own weight. The Sherman, far less powerful on paper, succeeded because its systems were balanced. It did not excel in any one category, yet it performed dependably in all of them. The contrast became a topic of discussion within the Ministry of Armaments. Albert Speer, who had witnessed the Sherman's performance during the Hillersleben trials, ordered his technical staff to review the Kummersdorf data carefully. The reports reached him at a time when Germany was struggling to increase tank production under severe resource shortages and Allied air attacks. What he read confirmed what he had begun to suspect, that Germany's insistence on technical sophistication was undermining its war effort. Despite these internal realizations, public messaging could not reflect the truth. The ministry's propaganda department published an article in the newspaper Das Reich on June 27, 1943, describing the Sherman as one of the special accomplishments of North American industry. The wording was cautious but revealing. It praised the tank's mass production quality and called it a praiseworthy product of the North American steel industry. To readers, it appeared to be an objective analysis. In reality, it was an attempt to acknowledge the Sherman's success without admitting inferiority. Behind closed doors, the tone was different. Engineers and officers who had observed the testing sessions spoke privately about what they had seen. Some confessed admiration for the American approach to machinery. Others were uneasy, realizing that Germany had no means to copy it quickly. The country's industrial system was fragmented into small, specialized firms that could produce exquisite components but not standardize interchangeable ones. The Americans, on the other hand, had perfected mass production through decades of peacetime automotive experience. Field reports arriving from Tunisia and later from Italy reinforced what the Kummersdorf data had shown. German crews in North Africa had already noticed how easily the Shermans moved across rough terrain, while their own tanks overheated or suffered gearbox failures. Reports from Italian units in 1943 described American tanks climbing steep hills with little effort. The pattern was consistent. The Sherman's mechanical endurance was proving to be one of the Allies' greatest battlefield advantages. Speer's staff quietly commissioned a comparative analysis between German and American production methods. The resulting study revealed that a typical American factory could produce a complete Sherman tank in less time than it took a German plant to assemble a single Panther engine. Interchangeable parts, standardized tools, and simplified designs allowed the Americans to maintain both speed and quality. German plants, still relying on skilled craftsmanship and manual fitting, could not compete in volume or consistency. Among engineers, the realization caused what one official later called a silent crisis of confidence. The German tank program had always measured success in terms of firepower, armor, and top speed, tangible qualities that could be displayed in propaganda films and technical tables. Reliability had never been given equal weight. Now, faced with the Sherman's unbreakable record, those same engineers saw that they had been designing weapons for short demonstrations, rather than sustained combat. By late 1943, internal memoranda from Kummersdorf emphasized the lessons learned from the American tank. One report summarized the issue bluntly. The American armored vehicle demonstrates the advantage of industrial maturity over technical ambition. Their engineers designed for use, not for display. That line circulated quietly through engineering offices, and even reached some factory managers. It marked a rare moment of self-reflection within an organization built on pride and secrecy. Yet it was already too late to change direction. The Panther and Tiger programs were too deeply embedded in the armaments system to be redesigned for simplicity. Factories were committed, blueprints finalized, and production lines fixed. The most the engineers could do was attempt to improve reliability, piece by piece. Stronger gears, better cooling, minor adjustments to ease maintenance. But the fundamental problem remained. Germany was trying to perfect machines it could not keep running, while the Americans built machines that simply refused to stop. By the end of 1943, War Daddy II had become a legend inside Kummersdorf. The tank had been tested, disassembled, and reassembled so many times that it was almost part of the laboratory itself. Mechanics used it to train new technicians, and visiting officers often asked to see it for themselves. Many left the proving ground with the same quiet impression. The Americans had achieved something that Germany, for all its brilliance, had failed to master: true mechanical reliability on a mass scale. The quiet shock of Kummersdorf was not a single revelation, but a gradual awakening. The engineers had not just tested an enemy tank, they had measured the strength of an entire industrial system and found their own wanting. As the testing at Kummersdorf continued through the summer of 1943, reports from the front lines began to mirror what the engineers had already seen in the laboratory. In every theater where the Sherman appeared, North Africa, Italy, and the Eastern Front, German soldiers found themselves facing an enemy machine that behaved differently from anything they had built. The Sherman was not the heaviest, nor the most powerfully armed, but it was always there, moving, climbing, advancing, and returning to fight again the next day. German tank crews who captured or inspected these vehicles often remarked on their mechanical endurance. Field workshops discovered that even Shermans, which had taken combat damage, could often be repaired and returned to service within hours. Engines restarted without difficulty, transmissions remained intact, and spare parts seemed to fit perfectly from one tank to another. This was something entirely foreign to German experience. In their own armored units, mechanics had to file, grind, and adjust parts by hand to make them fit. The idea that an engine from one factory could be bolted into a hull built by another without modification seemed almost unbelievable. Letters from German officers in Italy described the same impressions. One Panzer commander wrote that American tanks could climb slopes that German engineers had declared impassable for tracked vehicles. Another report noted that the Sherman could drive long distances over rocky terrain without breaking suspension springs or overheating its engine. The consistency of these observations forced the German command to confront an uncomfortable truth. The Americans had built a tank that could operate continuously, while German tanks had to be treated like delicate machines. By late 1943, the Wehrmacht began to experiment with using captured Shermans in its own units. Whenever a vehicle was seized intact, it was sent to local maintenance depots for quick inspection and then pressed into service. Unlike captured Soviet or British tanks, which usually required extensive modification, the Sherman needed almost none. German crews discovered that its controls were easy to learn, and that basic mechanical training was enough to keep it running. The manuals, when translated, surprised technicians with their clarity and simplicity. One German mechanic commented that the instructions read more like those for a civilian truck than a combat vehicle. The first large-scale use of captured Shermans took place on the Eastern Front, where Soviet forces received thousands of them through Lend-Lease. German units facing the Red Army began to encounter not only T-34s but also American-made tanks bearing Soviet marking. Whenever these were captured intact, they were sent to the nearest field workshop for evaluation. Reports from these workshops confirmed what the Kummersdorf engineers already knew. The diesel-powered variants, particularly the M4A2 with the twin General Motors 6046 engine, were exceptionally fuel-efficient and resistant to wear. Even after heavy use, they required minimal servicing. For German troops operating in extreme cold, the ease with which the American engines started each morning was both impressive and discouraging. In occupied Italy, the same pattern appeared. German troops advancing through the mountainous terrain after the Allied landings noticed that the Shermans could maneuver along steep roads that the heavier Panthers and Tigers could not safely use. The Americans moved their tanks with a freedom that surprised observers accustomed to mechanical limits. When one German division captured a small number of Shermans during the winter fighting of 1943, they found them ideal for reconnaissance and escort duties, roles where reliability and mobility mattered more than armor or firepower. The engineers back in Germany received these field reports with a mix of pride and frustration. On one hand, the data confirmed the accuracy of their own findings. On the other, it demonstrated that the weaknesses of German designs were now costing lives and battles. The mechanical failures that had been considered tolerable in testing were becoming catastrophic in the field. Panthers and Tigers often had to be transported by rail for long distances, as their transmissions and final drives could not survive extended road marches. Some divisions began to keep recovery vehicles permanently assigned to tank companies, expecting breakdowns before every major engagement. The Sherman, by contrast, rarely required such precautions. American and British armored units could move for hundreds of kilometers without significant losses to mechanical faults. The contrast in mobility had direct tactical consequences. Where the German units were forced to halt for maintenance, the Allies could keep moving, choosing the time and place of each encounter. It was not just a question of numbers or fuel. It was a question of confidence. Crews who trusted their machines could fight aggressively. Those who feared another breakdown fought cautiously, conserving their vehicles more than their strength. By early 1944, even German commanders began to acknowledge this reality in official correspondence. General Heinz Guderian, Inspector General of Armored Troops, wrote in one report that improving mechanical reliability had become a question of survival. He urged the Armaments Ministry to prioritize simplified systems and longer-lasting components. But the industrial situation made such reforms nearly impossible. Factories were already under strain from bombing, labor shortages, and material scarcity. Meanwhile, captured Shermans continued to serve quietly in German hands. Perhaps the best documented example occurred in January 1945 during Operation Nordwind, when the 10th SS Panzer Division captured a dozen M4A3 Shermans near Hatton and Rittershofen in Alsace. The tanks were reformed into a temporary company and used in combat. German crews praised their reliability, reporting that they required little maintenance despite weeks of constant movement. In the chaos of the final months of the war, those Shermans performed better than many of the division's own vehicles. By that point, the engineers at Kummersdorf no longer needed more data to understand what had happened. The frontline experience confirmed everything they had discovered in their tests. The Americans had built a machine that reflected their industrial reality: vast production capacity, standardized manufacturing, and decades of automotive experience. Germany had built machines that reflected its tradition of craftsmanship. Technically brilliant, but fragile and costly, the lesson was now painfully clear. The battlefield favored the tank that could reach it. Every Sherman that arrived ready to fight outweighed any number of German tanks stranded by mechanical failure. Firepower and armor could win individual duels, but reliability won campaigns. The Sherman's endurance had become not only a technical achievement, but also a strategic weapon, one that the German engineers at Kummersdorf and the soldiers in the field could neither ignore nor match. By 1944, the contrast between German and American industry had become impossible to ignore. The engineers, who had studied the Sherman at Kummersdorf, understood that what they had seen inside that single captured tank was not an isolated success, but the reflection of a vast, disciplined industrial system that Germany simply did not possess. The war in North Africa and Italy had already shown what this meant in practice. Now, as the fighting spread across Europe, it became clear that the outcome of the tank war would not be decided by design, brilliance, but by industrial maturity. In the United States, the principles that made the Sherman reliable were the same ones that had defined the country's automobile industry for decades. Companies like Ford, Chrysler, and General Motors had been building vehicles for ordinary citizens since the early 20s. Their factories operated on assembly lines, using standardized parts and streamlined procedures. Every bolt, bearing, and gear followed specifications that allowed them to fit anywhere, no matter who made them. When war came, that civilian experience was transformed almost overnight into military production. The same techniques that had produced millions of cars now produced thousands of tanks, each one interchangeable with the next. In Germany, the situation was the opposite. Before the war, automobile ownership had been rare and car production limited. Even the Volkswagen project, intended to bring affordable cars to the public, had produced fewer than 1,000 vehicles. The country's industrial strength lay in craftsmanship and precision, not in mass production. Factories were smaller and more specialized, relying on skilled workers to hand-fit components that were rarely identical from one batch to the next. When this system was redirected toward military production, it produced machines of impressive complexity, but at terrible cost. German tanks like the Panther and Tiger were masterpieces of engineering on paper, but each one was almost unique. Parts built in one factory often did not fit those built in another. Assembly required expert machinists, and repairs in the field demanded specially trained mechanics. Even when everything worked, the tanks were delicate and demanding. They could fight effectively, but they could not fight continuously. Every kilometer of movement consumed valuable component life, and every breakdown drained scarce resources. Meanwhile, across the Atlantic, American factories were producing Shermans faster than Germany could replace its losses. At its peak, U.S. industry delivered more than 2,000 tanks per month. The vehicles rolled out of assembly lines already tested, painted, and equipped, their parts interchangeable from one manufacturer to another. The Lima Locomotive Works, Pressed Steel Car Company, and Detroit Tank Arsenal all produced variants that could share components freely. A transmission made by Buick would fit perfectly into a hull built by Chrysler. This level of standardization was unheard of in Europe, and it gave the Allies an overwhelming logistical advantage. The difference extended beyond quantity. It shaped the entire way each army operated. American armored units could maintain their vehicles in the field with ordinary mechanics, Using standard tools, spare parts were packed in crates, labeled with universal codes that fit every Sherman in service. German divisions, by contrast, required technical experts for nearly every repair. Field workshops needed machine tools to grind, fit, and modify parts by hand. The loss of a skilled mechanic could cripple an entire battalion. The effects of Allied bombing made the situation worse. In April 1944, British bombers struck the Maybach engine plant at Friedrichshafen, destroying the facility that built engines for the Panther and Tiger. The same raid damaged the ZF gearbox factory, halting production of transmissions for months. German industry struggled to recover, and when it did, quality had fallen sharply. Slave laborers, forced to work under brutal conditions, resorted to acts of quiet sabotage, leaving cigarette filters in oil lines, assembling parts without proper clearances, and deliberately misaligning gear housings. Each small act made already fragile machines even less dependable. American production, by contrast, continued uninterrupted. Factories in Detroit, Cleveland, and Chicago ran around the clock, staffed by well-trained workers who were paid fairly and motivated to contribute. The result was not only quantity, but consistency. Each new Sherman met the same standard as the last, and spare parts arrived at the front in sufficient numbers to keep damaged tanks running indefinitely. The engineers at Kummersdorf studied this industrial gap with growing respect. They knew that Germany's technical knowledge was not inferior. The difference lay in how that knowledge was applied. The Americans had learned to balance performance with practicality, to value simplicity over complexity, and to trust the process of standardized production. Germany, by contrast, still treated each tank as a work of art, individually crafted, impressive to behold, but unsuited to the relentless pace of modern war. Internal memoranda written in late 1944 reveal the growing despair among German armament planners. They could no longer ignore the data. American tanks not only outnumbered theirs by 5-1, but also remained operational far longer. On average, a Sherman engine lasted more than 3,000 kilometers, while a Panther's rarely exceeded. Transmissions in German tanks continued to fail under stress, and final drives often disintegrated after less than 200 kilometers of heavy use. The contrast became most visible during the Allied advance through France. After D-Day, as German units withdrew eastward, hundreds of Panthers were abandoned on the roadside, not destroyed by enemy fire, but by mechanical failure. American troops, advancing behind their own armored columns, noticed the pattern immediately, while their Shermans advanced steadily, refueled and serviced at roadside depots. German tanks lay crippled by broken transmissions and burned-out engines. The battlefield itself became evidence of the industrial war. Germany could not win. By late 1944, German engineers no longer argued about the Sherman's quality. They understood that its success came not from superior design, but from a design that could be produced, maintained, and trusted. It represented a form of strength that could not be measured by armor thickness or gun size. It was the strength of a nation that had mastered not just invention, but production. A nation where the factory, not the workshop, had become the true arsenal of power. For Germany's engineers and industrial planners, the realization was painful, but inescapable. The war had begun as a contest of technology and tactics. It was ending as a demonstration of industrial civilization. The Sherman was proof that engineering brilliance meant little without manufacturing discipline, and that in modern warfare, the most advanced machine was not the one with the best specifications, but the one that could always move when it was needed most. By the summer of 1944, the difference between the Sherman and its German counterparts was no longer theoretical. It was visible on every battlefield. As Allied armies advanced across France, the reliability gap determined who could fight and who could not. German commanders repeatedly reported that their Panther and Tiger tanks broke down during marches, sometimes before they even reached the front. Engines overheated, transmissions jammed, and final drives shattered under stress. Recovery crews worked endlessly, but spare parts were scarce, and many tanks had to be abandoned. In some units, fewer than half of all armored vehicles were operational at any given time. The Allied experience was entirely different. Sherman units could march hundreds of kilometers with minimal losses. Mechanics replaced parts quickly, using standardized components that fit every vehicle. Crews trusted their machines and planned operations without fear of constant mechanical failure. This reliability allowed Allied forces to maintain momentum, advancing day after day, while German divisions struggled just to keep their tanks moving. Captured Shermans in German service confirmed the same pattern. Units that used them found they required far less maintenance than their own Panthers. In the final months of the war, some German officers openly admitted that the American tanks were the most dependable machines they had. By early 1945, the outcome was clear. Superior firepower and armor meant little if the tank could not reach the battlefield. The Sherman's consistent performance, the result of sound design and industrial discipline, gave the Allies a steady, unstoppable advantage. Germany's mechanical failures, multiplied by shortages and overcomplexity, turned its finest weapons into immobile burdens. In the end, reliability itself had become a weapon, and it was one the United States had mastered completely. When the war ended in 1945, Germany lay in ruins, and its once formidable armaments industry had collapsed. But among the wreckage, a few surviving engineers and officers carried with them the detailed technical reports from Kummersdorf, the same studies that had documented the Sherman's endurance and the failures of Germany's own designs. Those reports would quietly influence an entirely new generation of engineers in the years to come. In the 1950s, as West Germany rebuilt its military within NATO, the new Bundeswehr sought to design a modern main battle tank. Many of the engineers involved had worked during the war or studied its lessons closely. They remembered what the tests at Kummersdorf had revealed. Reliability, maintainability, and standardization mattered more than size or theoretical performance. The new vehicle would have to embody those principles. The result was the Leopard 1, developed in the late 1950s and introduced in the early 1960s. Its designers focused on practical engineering rather than excessive complexity. The powertrain was robust, built with generous tolerances that allowed easy field repair. Components could be removed quickly using standard tools, and many systems were modular, allowing upgrades without redesign. The tank emphasized mobility, reliability, and ease of maintenance, values that directly mirrored what the German engineers had once admired, reluctantly, in the Sherman. The Leopard 1 went on to become one of the most successful tanks of the Cold War, serving in more than a dozen armies and remaining in use for decades. It represented not only technological progress, but also a philosophical shift. Germany had moved away from the pursuit of mechanical perfection that had doomed its wartime tanks and embraced the practical, industrial mindset that had made the Sherman so effective. The lessons from Kummersdorf thus outlived the war itself. They showed that true strength in armored warfare does not come from complexity or size, but from dependable engineering that soldiers can trust. For the post-war German designers, this understanding became the foundation of their success, a quiet acknowledgement that even in defeat, knowledge gained from experience can lead to lasting progress. The story of the captured Sherman, known as War Daddy II, began in the Tunisian desert, but its meaning reached far beyond that battlefield. When German engineers first rolled it onto the testing grounds at Kummersdorf, they expected to find a crude example of mass production, a machine inferior to their own. What they discovered instead was a revelation that shook their confidence and changed their understanding of modern war. The Sherman did not impress through raw power or heavy armor. Its strength came from something far more important: dependability. It was designed to start, drive, and fight under any conditions, and to keep doing so with minimal attention. Every system inside it, the engine, the gearbox, The suspension reflected a clear philosophy: build it simply, build it strong, and make it easy to repair. That philosophy came from America's industrial maturity. The United States had decades of experience in mass-producing reliable automobiles, tractors, and machinery. Its factories could create thousands of identical engines, transmissions, and spare parts, all perfectly interchangeable. When war came, that same system was turned toward tanks, and it worked. The Sherman became not just a vehicle, but a symbol of a nation's industrial discipline and organization. For Germany, War Daddy II revealed what its engineers had long overlooked. Precision without practicality was a dead end. The Panther and Tiger might have been masterpieces of design, but they were fragile, expensive, and slow to build. The Sherman, with its modest specifications and simple construction, could be repaired anywhere and produced everywhere. It was not perfect, but it was always present, and in war, that mattered most. By the final year of the conflict, thousands of Panthers and Tigers had been abandoned due to breakdowns, while Shermans continued to roll across Europe in overwhelming numbers. Every tank that reached the battlefield became proof of a simple truth: reliability was a weapon in itself. The engineers at Kummersdorf had measured it in test reports. The soldiers at the front had lived it in battle. After the war, the lessons endured. The new generation of German designers, who built the Leopard 1, applied what they had learned from that single captured tank. That lasting strength lies in simplicity, maintainability, and balance. Those ideas, born from the study of an American machine, would shape armored vehicle design for decades to come. Today, the story of War Daddy II stands as a reminder that technology alone does not win war. It is the combination of smart design, organized industry, and reliability under pressure that decides success. The Sherman's legacy was not about being the most powerful tank, but about being the one that kept moving across deserts, across Europe, and into history.